Hi everyone, welcome and thanks for joining us for this webinar on advancing fish-safe hydropower turbine design. My name's Harry Driscoll. I'm the sales manager here at Natel, and I'm joined today by our CEO, Schneider. And now I can hand over to Gia for the presentation. Thanks.
Thanks very much, Harry. Thanks everybody for joining to learn a little bit more about what Natel is doing to advance the hydropower industry with respect to fish-safe turbine design. As a little bit of background on Natel, we're a California-based company, about 30 people, and our focus really is in how can we, through our work in sustainable hydropower, tackle the twin challenges of climate change and biodiversity. Just as a little bit of context for our work in hydro and our focus on fish-safe turbines, I think it's helpful to look at a few things. So one is hydropower plants obviously are on rivers. Rivers have fish, and in particular, if you look at where we have the large existing installed base in the United States, Canada, and Europe, there's a lot of overlap, particularly with migratory fish species. And so therefore, there's an increasing focus and requirement to provide for safe passage of fish. And our focus is specifically on safe downstream passage of fish. In addition, because these are large existing installed fleets that have been here for quite some time, we have a lot of older plants that are facing requirements to modernize and upgrade so that they can be an important part of our generation fleet for decades to come. And high performance fish safe turbines, that really is a way for owners to have a lowest total cost approach to both implement modernization and upgrades and at the same time meet some of these more stringent environmental compliance obligations. So our focus really is in the hydraulic design of high performance fish safe turbines. As a team, we do that design, have done a lot of work kind of very deep in the science of these blade shapes. And we provide engineering services to primarily owners, utilities, IPPs, developers, et cetera, to help owners understand what the options are to implement high performance fish safe turbines and what the economics of that path could be. We have in California one of the few labs that we're aware of that is able to do both scale model performance and fish passage testing simultaneously. We're able to perform those tests in compliance with, on the performance side, with standards like PTC 18 and IEC 60193. And also prove out fish passage performance as well. And then what we do is we partner with existing turbine manufacturing companies to make the turbines that result from this design work. To dive a little bit further into kind of these twin pressures of modernization and environmental requirements, zooming in specifically to the data set in the United States, a couple things are, I think, important to understand. So if we look at the existing installed base in the United States, and we look in particular at that installed base that is under 40 meters of head or about 130 feet of head, that's about half of the fleet. The reason why we focus on that head range is because over 40 meters or 130 feet, certain other types of effects, particularly around pressure and barotrauma, become the dominant force versus mechanical strike. And I'll get into this a little bit more in a couple slides. And so our focus, where our solutions really apply is under 40 meters, under 130 feet of head. But that's about half the fleet in the United States. And then if we look at the age of that fleet, the majority is over 40 years old. The average age of the fleet is 65 years old. So again, we've got this real requirement here for modernization and upgrades. And that modernization and upgrade scenario is coinciding with a wave of relicensings as shown in the chart on the right. And we're really quite early in this push on relicensings where plants will be going through that process with the Federal Energy Regulatory Commission. And that really is where we're seeing a lot of the imposition of more, again, modern requirements around fish passage. So to then dig a little bit deeper from a technical perspective, I think another thing that's important to understand in the fleet is that the majority of these megawatts in this lower under 130 feet of head space have turbines that have fairly high tip speeds. And this is an important thing to understand because this is really critical when we think about how do we actually design true like for like drop-in replacements of fish safe turbines with respect to older traditional units, knowing that we really need to respect the performance and operating characteristics of what currently exists. In terms of what impacts fish in traditional turbines today, again, under this 40-meter, 130-foot head range, is really mechanical impacts, particularly with respect to blade strike. So for Francis units, blade strike's the primary mechanism of fish mortality and injury. And in propeller and Kaplan units, fixed pitch or variable pitch units, really it's a mix of both the blade strike and grinding, where you have pinch points. And so our focus then of design has really been keeping in mind we need to design for high tip speed. So we want machines that can spin fast, but we also need machines that can be very safe for fish passage. That really leads to two very specific characteristics of the blades that we design. One of those is that these blades have a very thick leading edge. That thick leading edge basically creates a stagnation zone ahead of the blade. And that stagnation zone acts to deflect fish as well as debris around the blade as opposed to having a direct strike. And then the other critical part of the design is that as we go from the hub to the tip, we want to maintain a uniform high survival rate for fish. And so we take that tip and we slant it forward. And what that does is that allows us to keep high tip speeds, but as fish interact with the blade out at the tip, they are seeing more of a glancing interaction as opposed to a direct interaction. And those two things combined, so the thick leading edge and the forward slant of the tip are like the two kind of critical ingredients, if you will, to being able to design these blades that are, again, highly fish safe as well as high performance. Diving a little bit different of flavor on why speed is such an important requirement, technical requirement here. So the data on this chart comes out of a number of studies that have been done across existing units in the existing fleet, looking at passage survival rates, within these existing conventional units. And when we, from the chart a couple slides ago, what we know is that most of the megawatts really are in the 20 to 35 meter per second tip speed area. The reality of the work that has been done to date on more fish-friendly turbine types have generally been in the space where the turbines spin more slowly, right? So like the VLH or the Alden unit, these are slower tip speed machines. And so there's been a bit of a struggle of that existing technology to really address the technical requirements of the majority of the megawatts of the existing fleet, where we really have to be able to have machines that can spin quite fast. And what we've done with our work is we've now shown outstanding results with respect to fish passage performance at very high tip speeds. Those are the two orange figures on the graph above. In addition to fish safety, we obviously care about performance as well, because at the end of the day, from a hydropower plant's perspective, we really want to maximize power generation and operational flexibility. And here, the work that we do on the rest of the blade design is all focused on very conventional metrics around capacity, efficiency, and resistance to cavitation. And again, the test facility that we have in Alameda allows us to do testing on the performance side in compliance with PTC 18 or IEC 60193 standards to then have the data and the confidence that these shapes deliver performance metrics that meet industry needs along with the fish passage survival. Another interesting element of these shapes are that they are also very resistant to abrasive erosion. So the same elements of the blade design that help these turbines pass fish safely also help them be very robust to passing debris. And we've actually done some tests specific to abrasive erosion. And what we found were that these style blades are 6 times more resistant to material loss than traditional thin blade shapes. So the natural question might be, okay, all this sounds interesting, but where can I apply these designs? What has been done already? And for my particular plant in question, can I apply these designs? So to give you a feel for that space, basically, again, there's a head limitation, so 40 meters, 130 feet. If you have a plant that's under that head rating, then these shapes are very applicable for your plant. And we have designs that work for Francis, Kaplan, and propeller, so fixed pitch or variable pitch machines. We have a number of existing installed units shown in blue, and then the orange units on the graph here are designs that have been completed for different owners. They are not yet physically installed, where they're just the designs themselves have been completed. And again, we work with existing turbine manufacturers that actually make the equipment. What this means from an owner's perspective is that if you have an existing powerhouse and you are, facing this combination of modernization and fish passage, natural questions are, can I undertake an upgrade? Will I lose power output? What's involved in actually doing this? And again, every project we go through an effort to do the design specifically, but from the work that we've now done with a number of owners, it is now possible to design runner replacements or turbine replacements, could be either, where the replacement with a FishSafe unit delivers the same energy production with very good cavitation resistance, where the unit is fitting into the existing civil works. The drawing that's actually shown here is abstracted from a real world customer project, where they are keeping their generator, their thrust bearing, the discharge ring, the water passageway, the draft tube, all of that remains unchanged, and it is just a runner replacement. This is literally a like for like replacement. Same power capacity, same power performance, same operational flexibility as the existing old conventional unit. They will post installation have a hydropower plant that performs as it performed, but with fish safety. This type of plant is not a plant that really is amenable to screening. It passes a lot of flow. To put this into context of some numbers, comparing against perhaps maybe the conventional approach that is often being looked at right now, which would be screening and bypass. A really important element in the economic analysis is the size of the plant, and in particular, the amount of flow that the plant passes. And what we have found is that for plants with small flows, so let's say less than several hundred CFS, maybe single digit to maybe 10 CMS. So under that range, those are quite small plants, and it may be the case where screening is a more economic option. Just again, it's not a lot of flow to screen and much more amenable to that solution. But the reality is that the vast majority of the megawatts in the hydropower fleet come from plants that are passing much larger flows. And certainly once we get up over about 1,000 CFS or 30 CMS of flow, we really get into the range where screening becomes increasingly expensive, and the operational complexity imposed by screens to keep them functional on an ongoing basis for the upcoming life of the plant, again measured in decades, can be quite challenging. So this example here is a mid-teens megawatt plant passing about 7,000 CFS, almost 200 CMS of flow. And the bottom line is that when we look at the economic comparison of screens plus a bypass versus replacing with FishSafe units are a clear economic winner. And that's a result of a combination of both being cheaper from a CapEx perspective, but also importantly reducing risk and cost around O&M, and having a better bottom line from a revenue production as well as plant operational flexibility. Now dig into and highlight a couple pieces of the work that we've done, just to run through some of the fish science as well as field installations and design work. I'll start first with a little bit of an overview of our test facility in California. I mentioned this a little bit before, but just to zoom in a bit more detail. This is a pretty unique facility as far as what we are aware exists in the industry, in the sense that it allows us, again, to do combined 60193 or PTC 18 compliant performance testing, as well as scale model fish testing on the same facility. In particular, on the fish passage side of things, it's set up with transparent runner housings and high-speed camera, which allows us to capture in very, very high detail what is actually happening to the fish as they go through these turbines. So of course, we're doing other things like having appropriate test and control populations, monitoring the condition of the fish before they go through the test, after they go through the test for a full 48-hour hold period, et cetera. But also with this facility, we're able to actually see in very great detail what is actually happening to the fish as they go through the turbine directly. Now, to run through a couple of the results across a number of different fish species, we've done a lot of tests, for example, with eel. This particular one highlighted here we were fortunate to be supported by some funding from the U.S. Department of Energy. This work was also then subsequently published through a peer-reviewed process with the American Fisheries Society. We did 2 different types of tests. We did just single passage 48-hour hold with 100% survival. We also did a separate set of tests where we simulated the real world situation where you have cascades, multiple hydro plants down a river system. So we did repeat passage tests. So passage, 48-hour hold, another passage test, 48-hour hold, and also saw 100% survival from that. And if you look on the video here on the right-hand side, you can see the eel going through right there. There's a lot of video on our website too, if folks want to, dive deep into that. Next test to highlight here is one. This is actually one that we did in the field at a plant in Maine. And here, the species that we were testing were alosines, a very, very fragile fish species to test with. And we were able to show 98 to 100% immediate and 48-hour survival on a control adjusted basis from the fish going through this. Again, in the video here on the right-hand side, you can see the fish passing through the turbine right there, right there, right there. There were a lot of fish going through the turbine, so a lot you can capture on video. And again, this work was subsequently published in a peer-reviewed process with the North American Journal of Fisheries Management. The reason why we have a big focus on doing these kinds of tests and then putting them through the peer-reviewed process to publish is because in terms of establishing the integrity of these fish passage results in a manner that is sufficient to meet regulatory scrutiny, the peer-reviewed scientific process is clearly where we needed to go. The next one is, this is passage of rainbow trout as a stand-in for salmonids. So we've actually done, in the field, we did testing with rainbow trout. This was at a plant up in Oregon called Monroe. We have also done testing in our lab facility in California with coho salmon smolt. So we have done both trout as well as true salmon smolt tests. So now moving to projects where we have completed design. This is just to give an example of some of the range of work that we're doing with a number of different owners. And so the first example here is a plant with multiple Kaplan units. And the goal here is to get 96% survival for up to 40-centimeter fish and greater than 98% for eel. Important requirement around efficiency and some specific flow characteristics. That's one example of a Kaplan design. In the middle is a propeller unit. This is one of the largest units that we have designed so far. This will again deliver greater than 98% survival for eel on a fixed pitch machine, 92-93% peak performance or efficiency. Just to give a range of the different types of designs we do. We have several smaller projects that have been installed that have now been operating for a number of years, just establishing good, reliable plant operations, 2 in the United States, 1 in Austria. And so our focus again is to create turbines that deliver true, very high levels of safe fish passage, but also meet the plant requirements of the existing fleet. To approach these basically as modernization projects where you're just replacing the runner, just replacing the turbine. Typically, we start with what we call design feasibility study, just to put this into a specific action item. What practically do we do? Often what we do is we'll engage with an owner who's now facing a combined question of, I've got a modernization and a CapEx plan. I also, have concerns. Maybe they exist today because I am in a relicensing today, or I already have license conditions. Maybe I am thinking forward and, looking at, I have relicensing coming up. I have an old unit that is end of life today. What are my options to think about? So there's, again, many different types of scenarios. But what we generally can do is we come in, can take the existing characteristics of the plant and the units, and then do a preliminary hydraulic design of what a FishSafe solution would look like for that particular plant and for those particular units, and then provide a report that summarizes the expected range of performance from fish passage perspective, from a power output, cavitation, et cetera, efficiency perspective, as well as some preliminary indications around cost. Again, really appreciate y'all taking the time. Feel free to reach out to us as well. And yeah, have a great day, everybody.
Thank you. Bye.
How has Natel worked to share this tech with regulators? We have done a fair amount of work just to walk through a few things. In the tests that I went through, kind of scanned through here. And again, if you go to our website, which is natelenergy.com, you'll see a section for fish passage testing, and you can see links to a bunch of additional video, links to the papers that we have published. There's a lot of additional information publicly available there. prior to doing these tests, we reviewed these test plans with relevant agencies and obtained feedback on that. That was a critical part of our process to ensure that the type of data, the way these tests were conducted, would be informed by the kinds of data that regulators want to see in these tests. So that's step one. Then we conducted the tests, went through the process to publish papers on a number of these test results through the peer-reviewed process in fisheries journals. And that, again, is an important step to create an independent review that then regulators can look at. Obviously, not just a Natel review only, but to go through a true scientific review process. And then we've done a lot of work to reach out to primarily the federal regulators. So I think we have more work to do to reach out to the state level fish and wildlife regulatory agencies, but we have done a lot of outreach directly to the U.S. Fish and Wildlife Service and to the NOAA National Marine Fisheries Service to date. Outside the U.S., we have met with and have ongoing conversations to share the information about these test results, et cetera, in Canada, with DFO, fisheries regulator in Canada, and then with regulators in France, Germany, UK, Sweden, Switzerland, et cetera. So our focus is turbine design, and then we work with the turbine partner if there is a requirement as well for generators, powertrain, et cetera. So again, as a reminder, we do design, engineering, lab testing. Then we work with existing manufacturers. So for example, if you have a very large hydropower facility, then there are certain manufacturers who make large machines that we would work with. If you are a small or medium hydropower facility, then there's also a different range of manufacturers who we would work with depending on whatever is required for the owner and project location in particular. So these are units that are designed for the same operational life as a conventional unit is. And then from a maintenance requirement, same thing. There's no special maintenance requirement on these units. In general, actually, I think we would expect that these units should see stronger performance over their life, simply from the perspective, I can go back to this slide around the abrasive erosion point. These shapes are very efficient at shedding debris. And so again, debris is not the only thing that ages runners, right? Their cavitation performance is a really critical part of the design. But at the same time, from a debris management perspective, these blades are very resistant to debris. So in cases where you do have that as a concern, they actually should perform better than traditional thin blade designs, again, just based on some of the testing that we have done. With respect to other maintenance requirements, we have designs for Francis, fixed pitch propeller, and variable pitch Kaplan machines. And obviously the maintenance requirements for those different types of units vary, but those are all driven by the fact that the way you maintain a Kaplan unit is different than if you have a fixed pitch machine versus a Francis, and that is not tied to the shape of these blades.